Okay, this is lesson 3.3, day 1. We're going to spend 2 days on this lesson. Students, we're just working on this warm-up problem, solving a system of equation using an algebraic method of your choice. You can use substitution or elimination. All right, let's survey the crowd. Raise your hand if you decided to use substitution. 1, 2, 3, 4. Elimination? 1, 2, 3, 4. You didn't vote. Okay, right down the middle. I like the option of substitution because I see this 1 in front, so it would have been easy to solve this equation for x and substitute it. I did elimination, so that's just what I'm going to do. I find usually that's the method of choice, but it sounds like we're kind of split down the middle here. So keep in mind, it doesn't matter. We should still get the same answer. If this is confusing to you, feel free to rewrite that. Okay, it's just listing the variables in different orders. That's okay. So I decided to eliminate the y's. So I times this second equation by a negative 4 to make that a negative 2y. Okay, again, you could have done it differently. So I have my first equation there. Second equation, remember when you multiply, if you're doing an elimination process, you multiply by something, everything in there needs to be multiplied by that. So that gave me negative 4x minus 2y equals negative 8. Okay, so I'm going to go ahead and add those. Those will eliminate. I got negative 5/3. Same process, just have fractions. X equals negative 7. So I got x to be 21/5. 21/5 is not what we got.
Gotcha.
21/5, which is 4.2 if you wrote it as a decimal. Okay, if you did not get that, see if you can find a mistake. Now with elimination, you can go back and plug it into either equation. So I plugged it into this one right here, the one I did with blue, because I know x now is 21/5 plus 1/2 y is 2. All right, subtract over 21/5 times both sides by 2. I got y to be negative 22/5. Final answer, written as an ordered pair, we write x, comma, y. Okay, and again, it kind of depends how you did it. If you found y first and you got that wrong and you used that to find x, obviously your x is going to be wrong too. So try and follow your work and see if you can find your mistake. Same process, just little fractions. Okay, nothing you guys can't handle. But if you did not quite get there, see if you can find your mistake. Because I'm telling you folks, later in the week, we're going to start solving ones that are really a lot of steps and a lot more intense. And you have to be really good at like looking at your work and trying to find your mistake, because it can only take one small step in a very multi-step problem to mess everything up. So be really careful. Pay attention to the negatives. Be careful with all your multiplying and dividing. Check your work on a calculator too. I know a lot of you like to do the fraction stuff in your head, which is great. Great mental math skills. I love that. But if you're not quite sure, double check your math with the calculator, because we want to save ourselves making those mistakes. Okay, folks, here's a lesson for today. We're doing something called linear programming, and it's basically just a method of finding what we call optimization, which is like a highest point or a lowest point of a possible solution. And basically what linear programming is we find these constraints, which are basically all of these lines. Okay, we find all of these inequalities, and then we find our shaded region, just like we did in 3.2, where we graphed a bunch of systems of inequalities and found where their shading overlapped. And now we're kind of like applying it to like a context problem. of where in our solution do we have like the highest point, where do we have our lowest point. And a lot of these will do with like context and word problems of like, hey, here's our revenue, here's the constraints, like we can only work this many hours, we only have this much material. Of all these things factored in, we graph it, look at our feasible region, our shaded solution. We find all these points of intersections, they call those the vertices, and we basically just like plug them in to figure out, okay, what's our highest point in this possible solution, or maybe what's our lowest point if we're looking to try to like minimize cost or something like that. Okay, so just a lot of vocab here. So we call the feasible region just the shaded region. Okay, you can see that labeled for you right there. That's a feasible region. To find the optimal solution, you have to look at the vertices or the vertex of the constraints. That's just a fancy way of saying all of those intersection points of those inequalities. Okay, you can see those are vertex. The constraints are just the inequalities, these equations. And then to optimize, we'll take all of these vertices and determine which one is like our highest or our smallest, depending on like our objective. Okay. So use that as reference. If the feasible region is open like this, like it's not closed off, sectioned off, and forms like a shape, then we can't have a minimum or a maximum. It'd be one or the either. We're either going to have like a maximum, but there obviously is like no minimum in this example if it's unbounded. Okay, and if it was unbounded above, it would just have a minimum. All right, now we'll do so many of these kind of like together that the vocab will start to click for you. Today we're just going to stick with graphing ones, and then tomorrow we'll tackle some word problem ones. Okay, so here's kind of the step-by-step to solving these optimization with linear programming, as they're called. First off, we're going to define variables. That's more for like word problems. You're often going to have to write a systems of inequalities. Those are your constraints. So writing the systems of inequalities, all these equations for the lines with the constraints, if they're not given to us. We'll graph that. We have to find the feasible region where their shading overlaps. And then we'll have to find all of the vertices and where all those lines intersect. Okay, all our possible kind of like solution points, as I was saying. Find all of these. We'll do that from graphing. Then we have to determine with our objective function if we want this to be maximized or minimized, sub them into our objective function, and then figure out do we have the least or greatest result into the problem. That's more kind of like a checklist. Once we actually do a couple of these problems, you're probably like, what the heck is she talking about? Once you do some examples together, you'll be like, oh, okay, I understand. And if you ever need to look back and if you forget what to do after what step, that's just, I like that little layout for you. Okay, let's try one. And then, like I said, this will kind of make a little bit more sense. So this example, you can see they give me a system meaning more than one, okay? Linear inequalities. I actually have three. Kind of ignore this bottom one for a second. I have three inequalities. This one's a compound inequality, so that technically counts as two, right? This says y is greater than or equal to -8 and y is less than or equal to -2. So these right here are our constraints. These are what all of the basically like lines we're going to have to play into our graph. So I'm going to split this one, and we've done this before. We've graphed systems of inequalities. It's really the same thing. I'm going to break this one up into two. So I'm going to write that as y is less than or equal to -2 and y is greater than or equal to -8. So that's going to be easier for me to graph. Then I have y is less than or equal to x. Y is less than or equal to -3x plus 10. Those are all your constraints. That's our system of linear equalities. All right, this right here. So you haven't really seen this notation before, but that is our objective equation, and that'll come into play in like the very last step. So when you see the equation written with this notation, a function of x comma y, that's our objective. That's the one we're either trying to maximize or minimize, and we're going to do both. Okay. That's our objective equation. And obviously, it's also not an inequality, right? It's an actual equation. Your objective will be an equation. Everything else, your constraints will be inequalities. We'll have the symbols. Okay, so we're going to graph our constraints. We don't have to define any variables here. X and Y are defined for us. This isn't a word problem. Here's our system of inequalities, and now we're going to graph these. So y is less than or equal to -2. That's a horizontal line through -2. These are all solid lines. You don't have to worry about solid or dashed. You can add in your helper arrows as you go. We want to shade everything below it. Okay, first one done. Y is greater than or equal to -8. This line, horizontal line again through -8. Greater than or equal to would be everything above. Okay, so just with our first two constraints, we can see we have that section of our graph where our shading would overlap. I wouldn't recommend shading until the very end because we have 4 constraints here. All right, this next one is the line y equals x. Okay, so you can think about that one that has a y-intercept. However you want to graph this. Y-intercept of 0, 0. Slope of 1/1. So I would just start here at the origin. Has a slope of 1/1. So I kind of just put a few dots right there to get us started. And you can go as many as you'd like. I like to try and, you're going to have to find the intersections of your constraints. So I like to do as many points as I can that intersect my constraints because then it's maybe less math I have to do in the end. All right, so there's that line, y equals x. Now this one says I want to shade everything less than or equal to this line. So that'd be everything below. All right, now this line also in slope-intercept form for me. So I would just graph a y-intercept of 10, slope of -3/1. That's how I would graph that when it's in slope-intercept form. Y-intercept of 10, down 3/1. All right, this one is also less than. So I'd want to shade below this one. So this one's kind of like to the left would be below it. Okay. So right now I have to go basically like inside both of these lines and inside both of the horizontal lines. So my shaded region here would be this. And this is the only part you want to shade. This is what we call our feasible region. That little trapezoid piece. Okay, so right now you're like, this is what we did last lesson. Here's where the optimization comes into play. So after you graph the systems of inequalities, you want to find all of the vertices. So you want to find all of these points that border the shaded region. Okay, basically like all the corners. So I have 4 here at each kind of corner of my trapezoid. Now, this is what I was saying. The more like points you draw in, the easier it's going to be to find these intersection points. So I can see here clearly that those lines cross at -2, -2 for that point right there. And this point over here would be 4, -2. This point down here, 6, -8. And this point down here, -8, -8. Okay, I always label them on my graph. If I didn't know for sure where they would cross, we could algebraically solve for it. Okay, I'm just going to show you one really quick. Let's say we have this line y equals x right here. And let's say I want to know when these two intersect. And I don't have colors here to coordinate this, but when would this intersect this? You'd want to solve them both for y, which is already done. and then set them equal to each other. Okay, so when would -2 set them equal to each other? -2 equal x. Well, there's not much to solve there, obviously, at -2. And then you could like plug it in here to get the other coordinate. So if you're not sure where they intersect, maybe a better example would be like these two lines. Well, we don't have to find those ones. If you're not sure, set the two equations equal to each other and solve. We can do another example later. Okay, there's all my vertices of the feasible region. So now what I'm going to do is I'm going to take my objective equation. I'm going to plug in all of those vertices into my objective equation. So we got the points. Doesn't matter what order you list them. -2, -2 was one of the vertices. 4, -2. 6, -8. And -8, -8. Okay, so obviously x comes first, then y. So I'm going to plug these all in to this objective equation, which is 5 times x plus 14y. So my first example, I plugged -2 in for x and for y. To save you some time, I got out -38. All right, next I'm going to plug 4 in for x, -2 in for y, and I got out -8. Next one, 6 in for x, -8 in for y, I got out -152. Oh, that's why I got out -82. Sorry, I listed them differently. 6, that one's -82. -8, -8. Plug in -8 for both x and y, and that one I got out -152. I just listed them in a different order. Okay, so if this is kind of like my objective equation, I want to find my max and my min, or my highest or my lowest value. And in this case of this list, guys, from -38, -8, -82, -152, what's the biggest number of that? -8. This right here is your max value. And it's at the point for -2. So of your solutions of that whole shaded region, that's the biggest solution point. And this is used, like I said, a lot of these are word problems, so kind of make more sense. Which of these is the lowest number? -152. There's your minimum value, and that's at the point -8, -8. Okay, so basically that's kind of like our extra step now, is we have to take that objective function and figure out our highest and our lowest. And today we're not going to do any word problems. We'll just kind of practice graphing these, finding the vertices, finding the maxes and mins. So of all those shaded solution points, -8 is our highest solution point of that objective equation. Okay. Any questions on that one? They're kind of fun, right? I like shading. I don't know why. It feels like coloring to me. Okay. Similar setup here. So my constraints are my linear systems. So this first one I'd break up again. Y is less than or equal to -5. Y is greater than or equal to -17. That just helps you graph it. Then we have y is less than or equal to 3x plus 19. Y is less than or equal to -4x plus 15. My objective equation, I see f of x comma y is 8x minus 3y. So that's the one I'm going to try to optimize. Find the minimum or the maximum. Alrighty, so when I go to graph my constraints, I see I have to graph y is greater than or equal to -17. So I'm obviously going to have to do some scaling on my graph. So I'm going to count up by 2s. No, I have to mark all of them. Let me just mark some. So I would be going down to -20. Okay, I'm not quite sure about my x-axis yet if I have to do any scaling, because my first two are just horizontal lines. Y is less than or equal to 5. So it'd be right in between -4 and -6. You want to use your straight edge on these two if you have a straight edge with you. Because we have to find intersection points. And then negative 17 would be right between negative 16 and negative 18. Okay, so again, we're going to shade less than that line at y equals negative 5 and greater than that line at y equals negative 17. Okay, now these are in slope-intercept form, so that's how I would graph these. I would graph this at the y-intercept of 19 and a slope of 3 over 1. Same with this one, y-intercept of 15, slope of negative 4 over 1. You can also make a table if you wanted to and get some other points. Okay, now we counted up by 2's on our y-axis. We got to be consistent with that. Okay, now I'm just giving you a forewarning, because this is exactly how I did this. I plotted my y-intercept at 19, and then I did my slope, and then I realized like my graphs are crossing like way out here. Okay, and that's just something you're gonna have to look at and use a little bit of like number sense of like, ooh, okay, I'm way off my graph here. So on my x-axis, I also ended up having to count up by 2's. You don't have to label all of them like I'm doing, just this is for sake of kind of showing you guys. Okay. So if I go to graph that third inequality there in my system, I have a y-intercept of 19, that'd be right here. Okay, now careful, when you do this slope of 3 over 1, remember, you're counting up by 2's on each of your axes. Okay? So it's easier for you to think, well, that's the same as going 6 over 2. Like you could do it that way, like go down 6 and then over a full box. Or, I mean, you can still do 3, down 3 over 1, down 3 over 1. Or you could go down 2. Oops, I didn't go down 3, that one. Hold on, let me do that again, sorry. Oh, it's positive 3. Oops, positive 3. Down 3. 2, 3 over 1 would be there. Down 3 over 2 over 1 would be there. Or you could go down 2, 4, 6 over 2. Does that make sense what I'm saying? So it's up to you. If you see this as, hey, I got to go 3 over 1, just remember you're counting it by 2's. So 3 over 1 would be there. Or you could go 2, 4, 6 over 2. And that'd be the same thing. Okay, so everybody should be crossing then. If you're doing your slope correctly, it should be crossing this horizontal line at -8, -5. All right, so make sure. And again, I caught myself. This is a positive through one, so you got to go down and left. And it should, again, cross at -12 and -17. Okay, so make sure you have those correctly. This is where you just have to be really, really accurate in your graphing. So that point should be where they intersect. Obviously, it's a little bit tougher with our scale, but be precise. It's part of math. All right, everybody okay with that? Should be crossing right there. Now I got to do this other line. Similar one here. This one has a y-intercept of 15. You're like, oh, we counted up by 2's, and then we have all these odd numbers. No worries. This one has a slope of -4 over 1. So we're going down 4. That's really 2 boxes over 1. 1. Or again, you could think of that as down 8 over 2. Okay, you should get these intersecting at 5, -5. Really hard to do up here. And again at 8, negative 17. This one's a little bit steeper. Okay, I'm going to say this again. If you're not quite sure where they intersect, you could just set these equations equal to each other. You don't have to write this down. Okay, and then you could just solve this. So I'm talking about this line and this line. Let's see, that'd be 20 there, 20. Thank you, 36. Negative 12. Okay. So that gives us the x value, negative 12. And then we can go plug it back in here. We get the y coordinate of negative 17. That's if you didn't know exactly where. But the more accurate are your graphing, I think there's maybe only like a couple problems in the homework where you might have to do that. But for the most part, they should cross at like exact points that you can find if you do precise graphing. Okay. Now, the objective part is you just plug all those points in. So let's split up the duty here. Okay, we got the points, negative 8, negative 5, negative 12, negative 17, 5, negative 5, and 8, negative 17. Okay, let's have you three, James, Carter, and Riley, you guys plug in the first point. Tell us what you get. Nick and Kayla, why don't you guys do this second point? Okay, we've already done it, hang tight. Connor and Mary Kate, you guys do 5, negative 5. Brayden, Alexis, and Sydney, you guys do this last point. I'm going to write out my work while you're doing that of just plugging all these numbers in.
Negative is negative. And it's 8 times negative 5. That's negative 3. It's negative 3.
This one would be positive.
Yeah. How? Oh, wait. Oh. What did I do? Oh, I did negative 5. I did negative 5.
Negative 5 is the y.
Oh, I wrote it down wrong.
Yeah, you might have wrote it down wrong.
I got it now, Mary.
Yes. And then what did you get? Did you do it?
Yeah, I told you.
Did you do it right? Did you do it?
All right, you three that did the first point, what'd you guys get?
Negative 49.
Me too, negative 49.
Yep.
All right. Kayla, you still crunching back there?
I got negative 45.
So you got Nick? Negative 45? Good. All right. Mary Kate, what'd you guys get?
55.
55? Brayden, I feel like you're a team captain back there. What'd you get?
115.
115. Okay. So there's all our numbers. Our highest is 115. So we would have a max. Oh, I forgot my red pen. Max at the ordered pair 8, -17. -49 is our lowest. We would have a min then at -8, -5. I didn't actually shade my feasible region. You can. Probably should shade this just for sake of what we're looking for. However, we're really just looking at those intersection points. But that right there is my feasible region. My vertices are those green points. My objective equation is the one that we're trying to optimize, find the highest and lowest. All my linear inequalities, those are my constraints. Okay, that's all kind of that vocab. Okay, that's basically the math of this lesson. Now what we'll do tomorrow, and you'll get some obviously work time tomorrow, is we'll do like a word problem, because this is where these comes up a lot. Because we're trying to like maximize here, what is this, skateboards, we're trying to like maximize the profit. Okay, so that's going to be like our objective equation. Yes, sir.
On that problem on the back, isn't that like 3x plus 19? Shouldn't the arrows be going outside? So why?
3x plus 19. Nope. So
Less than.
here, yep. So here's where it crosses the y-axis.
Yeah.
Which y values are less than? The ones on this side, below it, or the ones above it?
Yeah. That's. Oh. Wait. What aren't those? Oh. Okay.
Yep. Good question. And then, so I always look at the y-axis. I'm like, okay, the ones, because it's always less than the y values. Yeah, I didn't draw my helper arrows there.
All right.
Okay. Does that make sense?
Yeah, I got it.
Yeah. Sorry, I just glossed over those helper arrows, but put those in to help you with the shaded region. All right, I'm gonna pause this video recording.
I did a book this on there.